Welcome to my channel. In this video, I am going to discuss Perceptron and Adaline. This is the part 1. Here I will give you brief introduction about Perceptron and Adaline. In short, I can say the Perceptron and Adaline, these are old models of artificial neurons. I'll discuss what is artificial neuron later, but this is basically artificially designed to mimic our biological neuron. Okay. In this video, we'll try to understand the evolution of these models. Meaning is that from where it started and how it evolved over time and what is our current status or today's neuron. We'll try to understand all those things. What are the changes done? So this knowledge will obviously help us to understand the today's model. And you know that recently deep neural network is hot topic and everybody is interested to understand deep neural network. So if you have proper knowledge on these models, Perceptron, Adaline, and today's artificial neuron, then we can make our foundation to understand deep neural network. Thus, this video is very important. So I request all of you to follow this video neatly. Keep patience. Try to follow everything. Try to understand everything. And I hope it is not difficult to follow, but it is too much important. Okay, let us start. Before that, I'll give you the outlines of machine learning and data science courses in this channel. So here we'll discuss this Perceptron, Adaline, artificial neural network, backpropagation algorithm based on gradient descent algorithm. So you know that already we have discussed gradient descent algorithm in detail. So I'll request all of you to go through gradient descent algorithm, that part. That will be useful to understand this course. We'll discuss linear regression, polynomial regression, ridge, lasso, elastic net regression, all those things. Statistical decision theory, Bayesian learning, Bayesian network, everything will be discussed here. Then principal component analysis, partial least square, linear classifier, logistic regression, linear discriminant analysis, SVM, support vector machine, all those things will be covered here. Expectation maximization, EM algorithm, GAMM, Gaussian mixture model, and some introduction about reinforcement learning will be also discussed. And last but not the least, that is the deep learning. And I can say that is the prime focus of this course. Okay, so we'll cover all this topic, right? But what will be the next topic? Just this video I am giving you the brief introduction about Perceptron and Adaline. So I have not thought about anything about the next video. So I'll request all of you to give your opinion in comment section, which topic you want first. So I'll go with the majority. Okay. So please comment on this comment section, write on the comment section which topic you want to learn first. Okay. Then I'll decide. Okay. Let us start our discussion on Perceptron and Adaline. So what we'll do, we'll start with our biological neuron, then try to get the idea about artificial neuron. Okay, we'll try to understand what is the first model that is used to mimic this biological neuron. right? That is not Perceptron or Adaline. It is something else. So we'll discuss here that also. Now, first we'll discuss this biological neuron briefly. So in our biological neuron, we have these components. These are dendrites. These are dendrites. Okay, there are several dendrites, and here it is axon and axon terminals. Inside this is one nucleus, and this one is cell body. So what is the function of this biological neuron? That we need to understand first. So actually, this biological neuron is used to convey the message from outside world to our brain, or to convey the signal or the decision that is made in brain that should be conveyed to the end part, okay, effectors, that is called effectors, through these neurons. So two-way message, but this neuron is one directional only. Some neurons are there which will try to collect the information from outside the world, and it will try to send that signal through this axon and other neurons connected one after another towards the brain. This is one side, one type of neurons. Another type of neurons are there which are connected, dendrites are connected towards the brain. It will try to collect the decision that is taken by the brain. That information should be conveyed toward our body parts, right? Effectors like muscles, through this axon, all those things. So here the dendrites, they are basically the component which will receive the signal, okay, and in nucleus and body cell it is processed the signal. So there are several signals will be captured here through these dendrites, and they will produce one information, collective information here, and that will go through the axon, and then through this axon terminal it will be connected to another neuron, means dendrites of another neurons, and that, so it will exchange the information from axon to dendron through synaptic nodes. So in between these axon terminals and dendrites there are some chemical composition, those are called synapses, okay. So they can transmit the message from one terminal, axon terminal, to dendrites of next neuron. I hope you have understood the concept, the function of this biological neuron, okay. Now, how to model these things using our signal processing concept? So we know that in a system we'll accept few inputs and we'll produce certain output. So these are the inputs. So input signals will be captured through these dendrites, and the output will be delivered by this axon terminal. And this axon, this bar, this is just like a transmission line, okay, right. So first model, that is called McCulloch-Pitts Model, and this model was proposed in 1943. So you see, this is around 80 years ago. Today is 2020. Okay, in 80 years ago, this model was proposed. One model was proposed to mimic this biological neuron. Okay, that will be calling as artificial neuron. So model of our artificial neuron, the first model is McCulloch-Pitts. So what is this? So these are the inputs. As I've said that it should have certain inputs. So not only 3 inputs, but only 3 I have shown here. Basically, there are several inputs. So x1, x2, x3 up to xn. Suppose we can consider n inputs are there, but at the end it should produce a single output y. So this is our system. That system we need to design. Okay, so those inputs are collected and it will produce single output y. Okay, so what is the system? How to combine? So these inputs are connected here, and this here, this process, so actually this nucleus and cell body is considered here only. Okay, it will collect all the inputs and then it is processed and it will take one decision, and based on that decision the output will be fed to the next neuron. Okay, so this function here I'll call it G, one function to combine these all inputs, and F, another function which is used to take decision. So two functions will be used. So G actually linear combination will help us to get linear combination, and F is one function that is called decision function to get final output y. Right. Now we'll discuss this G and F function more in detail for this McCulloch-Pitts model. So this is the model. Now what about G and F? So G is very simple. So G will combine these all inputs x1, x2. Here I've considered only 3. So it is 3 inputs x1, x2, x3, the function of this input, and it will produce the linear combination. It's a weighted combination, and that output I'll call it G. Okay, so W times x1 and same weight W times x2 and W times x3, like that. Okay, so here one important thing is that in McCulloch-Pitts, these weights, all weights are given same, are made same, means all inputs are given equal importance. Okay, that is the important feature of McCulloch-Pitts. So in biology neuron, so obviously it is expected that all the dendrites should be identical. They should behave equally. Thus, all the link should have same weightage, W, W, and W. Okay, that is one important thing. And this output Z is then processed to give final decision. Okay, so here hard threshold function is used to obtain this final decision of y. So y equal to f of z, that is binary output, either 1 or 0. It is 1 if z is more than one threshold value theta. So z is more than equal to theta, then it is 1. Otherwise it is 0, means when z is less than theta, it is 0. Right? So this is the simple model. Now these equations, these two equations, we'll try to implement in a circuit form, okay, in better form. Let us see. So these are the equations. So one is linear combinations with equal weights, and other one is threshold function. So you see, this linear combination we can get. So if x1, x2, x3, these are the inputs, we can multiply with each weight. W is multiplied here. This W is multiplied with this input. This W is multiplied with this input. So here you will get x1 times W, or W times x1. Here you will get W times x2. Here you will get W times x3. So each component will get here. Then we need to combine it, just add it. Okay, so I need one adder. This is one adder. It will combine all those things. Okay, then we'll get this G. Then y is a function of this G. Then we need to use one hard threshold operator function. So this threshold value is theta. So when G is more than theta, then only it is 1. Otherwise it is 0. Okay, so this is your McCulloch-Pitts model. right? It is very simple model. It tried to mimic our biological neuron. You see why I'm saying that it is trying to mimic the biological neuron, because it will accept all the inputs, and all the inputs are given equal weightage, and then it will try to combine and take final decision, and that will be carried, it will be transmitted to next one, right? Now, what is the application of this artificial neuron, right? And before that, one thing I can discuss, that sometimes these multipliers we can remove it. Just we can consider one line here, these lines are there, it is coming to this error, and here we will mention this weightage W. Meaning is that this W is multiplied with x1, then it is coming here. This W is multiplied with x2, then coming here. So here exact value is W times x1, W times x2, W times x3, like that, right? Okay. Now, its main application is to design digital systems or logic gates. And it can also do binary classifications. So exactly, using binary classification only, we can design these logic gates. I'll give you some examples. So first example is OR gate, two input OR gate. Suppose I have only two input, x1 and x2, and output OR gate output is y. Okay, so if it is 0, 0, in first input is 0, second input is 0, then output is also 0, OR. So if any of these two input is 1, then output is 1. Okay, so if first input is 0, second input is 1, then it is 1. Or this first input is 1, next one is 0, then also it is 1. And if both are 1, then also it is 1. It implies that if any of these two inputs are 1, then it is 1. That is the concept of OR gate. Okay, now we can represent here. This axis I'll consider x1, this axis I'll consider x2. And this is the origin 0, 0. This is your x1 is 1 and x2 is 0. This is your x1 is 0 and x2 is 1. So 0, 1. And this point is both are 1 and 1. Okay. Now you see this pair 0, 0. This 0, 0 is here. That magnitude output is 0. I will indicate by white dot. And this pattern 0, 1. So 0, 0, 1 is this one, and that is also 1. Okay, that means this red. I have considered in red. Red means 1. Okay, 1, 0, similarly it is 1. 1, 1, it's also 1. So out of these 4 dots, 4 patterns, 3 dots are 1, means red, and only 1 dot is white, that is 0. Now we need to design a system to get this kind of output using this McCulloch-Pitts model. Okay, so what we can do, so here we can choose these values only. So this W, I have one option, we can choose the W, and one threshold parameter theta. So we can find these two values to make our system, that's all. So no more things are there. So generally we'll consider W as 1. All W, all weights are given as 1. Okay, and just we will consider one parameter, that is theta. So we'll adjust theta, right? So if I have two inputs x1, x2, so these two are added. So this weight is 1, this is 1. So it is here z is nothing but this x1 plus x2. That's all. So what is your z? In this case, z is simply x1 plus x2. Numerical additions. Okay, that I'll put it here. So if I take one more column, that is your g is equal to x1 plus x2. So this is, if you add these two, so 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is also 1, 1 plus 1 is 2. Okay. Now this is the output here, but here I want to get binary output y. That should be 0 and 1. And when z equals to 0, g equal to 0, then y equal to 0. And when g equal to 1, 1 or 2, then output Y should be all ones. Okay, so it shows that if I consider one threshold value theta equals to 1, then it is done. Can you notice these things? If I consider theta equals to 1, because you see this output Y equals to 1 if G is more than theta, more than equal to theta. So equal sign I have considered here, okay? And if G is less than theta, then it is 0. So when Z is 1 or more, then output is 1, thus theta equal to 1. So this is one choice, okay? We can fix theta equal to 1 and we'll get our desired system or gate, okay? So can you draw this line? You see, this line is corresponding to x1 plus x2 equals to theta, and theta is in this case 1, so this is the line. So minus 45 degree angle, okay, because weights are same, and this value is 1, is passing through 1, 0 and 0, 1. But this is not the unique solutions. We can have more solutions, more value for theta. So where we can place theta value? So you see, so I need to make output Y equal to 0 when Z equals to 0 only, G equal to 0 only. So if G is some non-zero positive, then also it will work. Because if G is non-zero positive somewhere here, right? And then if I consider these things, then obviously this theta value is some positive value within 0 to 1, then one equation will lie in this line, in this portion, but parallel to this line, obviously. So we can consider x1 plus x2 equals to theta, where theta is within 0 to 1, equals to 1, up to 1. So more than 0, but less than equal to 1, then so it is fine within this range. So it will give you OR gate. So it is not a unique solution. See, there's flexibility. You can choose different values of theta. It will give you OR gate. Right. Now similarly, you can design AND gate. Very simply. So 0, 0, 0, 1, 0, 1 is 0, 1, 0 is 0, and 1, 1. If both are 1, then only it is 1. That's how it is called AND. If A, x1 and x2 both are 1, then only output is 1. Okay, that I have shown here in this picture. You see 3 white dots corresponding to zeros. Okay, 0, 0, 1, 0, 0, 1 combination, and 1, 1, it is only the red. Okay, so I want to make this system. Now here again, you see G equals to x1 plus x2. And you know that x1 plus x2. Okay, so it is 0, 1, 1, and 2. No, that we have already seen. So when G equal to 2, then only output should be 1. That's all. Can you remember? So when G is less than 2, it should be 0, in other words. So we can fix our G, theta value, the threshold value, as 2 separately. So can I make theta equals to 2? So it will pass through this line. So including this point, because I have considered equal sign here, G is more than equal to theta. So when G is more than equal to 2, then it is 1, including this point. Okay. So this is not only the solution, obviously again. So if we can place one line in between here also, it will work. Okay. Then can you tell me what would be the range for this theta? Okay, we have seen that if the line, this line, that is what theta equal to 1, and this line is theta equal to 2. So obviously it is in between this one. Okay, so we can set one value x1 plus x2 equal to theta, and theta range should be within 1 to 2, and here I can put equal sign 2. That is fine. Okay, but don't put equal sign here. Then it will also include these things. Then this 3 will be, it will become OR gate. Okay, right. Now next one is, can we design XOR gate, 2 input XOR gate? So XOR gate, you know that exclusive OR only the last one, when both are 1, in OR gate it was 1, but that is excluded, that is made 0 again. So if one input is 1, then only it is 1. Okay, either x1 or x2 is 1, then only output is 1. That is called exclusive OR. So the output is 0, 1, 1, 0. Now can you design? So you see the constellation. So this is white 0, this is again white 0. Okay, and this is 1, this is 1. So these are the same group, and this is on the same group. Now can you consider one straight line to segregate these two patterns, these two groups? It is impossible. We can't make one line here. If I can place one line here, then all the three will come to one group. That is not the case. Again, I can't fit here. Again, these three will be one group. Okay. And if I consider this one vertical line, then these two will become one group. That is also not true. So we can place any straight line here to consider these two one group and this white two in one group. Okay. So McCulloch-Pitts model, this only one neuron, cannot be used to design this XOR gate. We can't design it because it is not linearly separable. Okay. So meaning is that by using one straight line, we cannot separate these two groups. Okay. So this is only one thing. Now, what is the limitation of this McCulloch-Pitts? Here you see all the inputs are given equal importance. So W, W, W. Okay, because all weights are same, thus all inputs are given equal importance. This is one limitation. So we cannot adjust, we cannot provide different weights for different inputs. But for biological neuron, it is good one, because in biological neuron, all the dendrites should be identical. So it is very close to our biological neuron. But according to our expectation, if we want to use this artificial neuron for our defined purpose, then this model is having some limitations. Okay, we want more flexibility. Okay, so these weights could be made different. Okay, so weights, again, one more thing is that these weights are fixed. You can't adjust it. So basically, in McCulloch-Pitts model, there is no learning rules. So no learning algorithms are associated with this model. It is not the concept, because biological neuron, it is not tenable. It is just a function. It will consider one element which will convey the message. That's all. It will not update its link or weights with times. It is not the case. So that's how these weights are not updated in McCulloch-Pitts model. However, in our artificial neuron, we want some learning rules to adjust these weights. And at the end, this threshold parameter is also you have to find out manually for McCulloch-Pitts model if you want to design a particular system, right? Okay, so we'll move forward. Now, one more thing, from this McCulloch-Pitts model, this threshold parameter is theta. And now you see what is the meaning of this threshold parameter. We'll try to understand more detail. So this output is y equals to f of g. So when g is more than theta, then it is 1. And g is less than theta, then it is 0. That is fine. So this one we can rewrite as, so that theta I can bring into the left side. So g minus theta is more than 0, same thing. And g minus theta less than 0. Right? Now, so I can subtract this theta first, then we can compare with respect to 0. Right? So what we will do, we have g value here, then we will subtract theta. So minus theta will be added with g, then we'll get another value. So it is u. so E equal to G minus theta, then we can use one Hart-Threshold operator, and that Hart-Threshold operator is around origin, means the threshold value is 0. It's always fixed. So we can consider that one threshold parameter, threshold function, is around 0 always, and we can add one component here, that is your minus theta. That should be added before that. It will work similarly. So this model could be replaced by this model, that one extra terms minus theta should be added here, and this threshold parameter will be around 0, mean threshold parameter will be 0 only. It is always around 0. Okay, so that we can do. So same thing I have done here. So minus theta is added here, and here I have considered one Hart-Threshold operator around 0, and this is called step function or Heaviside function, right? So more than 0, equal to 0, it is 1, and less than 0, it is 1. So unit step function. Okay. Now this minus, what is about this minus theta? So what is G? Is now basically this G is Wx1 plus Wx2 plus Wx3 minus theta. This is your G. Okay. So if this is more than 0, it is 1, and if this is less than 0, it is 0. So here minus theta, we can say it is a bias component. It is not depending on input. It is a constant always, and that is called bias. When all the inputs are 0, then also this value will be there. Okay, so minus theta is called bias, and this bias we can replace by one constant value. So I'll go for, instead of minus theta, I'll go for W0, similar to this weight W. So W0 is one constant value that is added here. So this W0 is added. So we can write W0 times 1 in a similar form, W into x1, W into x2, like that. So if I write in this in W0 into 1, then we can think this one as weight is W0 and input is 1. That also we can consider in that way, in similar way. So you see, this input is x1, weight is W, so here the value is Wx1. So here I want W0 only. So why not, I can consider input is 1 and weight is W0, so it will be in the same form. So that will be used. So here I can consider one constant input, in magnitude is 1 and weight is W0, that is added. So this is your entire linear combiner, followed by this Hart-Threshold operator around 0. That is the important thing. Okay, right. So we'll be using this concept for our Perceptron and Adaline. Now we'll start Perceptron and Adaline. We'll try to compare these two. Now Perceptron algorithm or Perceptron model is proposed by Rosenblatt in 1958. Okay, so you see this is also 2 volt, 1958. Okay, it is 43, after 15 years Perceptron was proposed, and whereas the Adaline was proposed by Bernard Widrow and Ted Hoff in 1960, almost at the same time. Okay, now what is the difference between this Perceptron and Adaline then? And you see this fellow, the Widrow, is very popular, so he contributed a lot in adaptive filtering, and they proposed least mean square algorithm. That is the most fundamental algorithm in adaptive filtering. Least mean square algorithm was proposed by Widrow. Okay, so we'll be discussing later. Now let us see what is Perceptron. So model is very similar to that one, McCulloch-Pitts. Only difference here is that the weights. So you see the inputs x1, x2, x3, xn are there, and one input, constant input is 1, and its corresponding weight is W0 I have considered here, and x1, weight is W1, X2 weight is W2, X3 weight is W3. Similarly, Xn weight is Wn. They are multiplied correspondingly and then they are added here. That will give you G. And then we'll use one threshold function. So here threshold function will consider bipolar. So this value is 1 and this value is -1. This is around 0. Right? So very similar. Now only difference thing is that here these weights are different. Not only different, they're adjustable. So how to adjust these weights? Okay, now you see. So these weights are adjustable. So how to do that one? Okay. So this output y, final output y. So final output will be either, so you see the final output. So y could be either 1 or -1, no other values. Okay. So this, because this is 1 or -1, right? So we can use this data set, this model, to separate two groups. Okay. So two groups that desired signal, desired value is could be D again, +1 or -1. It's a target. It is also called target. The target value could be +1 or -1. We'll try to match these two. So when this output, so we want that output should be close to this D every time for every data sequence. So this x1, x2, x3 up to xn, for this one set, I should have one corresponding value D. Okay. So this x1 to xn, these are called feature vectors. And for this feature vector, I should have one corresponding output, desired output, that is your D. Okay, so from this model, we want to get same output Y. So Y should be equal to D. So if there is any difference, that is the error. So E is difference between D and Y. Okay, so if any error is there, then we should use certain rule to tune these weights W0, W1, W of Wn, so that Y is coming closer to this D. Okay, so difference between D and Y is reduced. That is the objective, right? So what is the rule that will be discussed later? Fine. Now see this Adaline. So what is the difference? Now again, the similar structure, exactly similar up to this. So it's a linear combiner followed by one Hertzian operator. Again, W0 to Wn all are adjustable. Okay, but how to adjust it? The only difference is that now from here, from this G, we'll consider here. So this D and G, these two will be compared, and based on these two difference, we'll consider the error E, and using this error, we'll try to tune these weights. So here D is called desired signal or target. Okay, and you see this G value could be anything. Okay, it's continuous value, whereas Y is a quantized value. So thus this one is also called quantizer. So you can understand that Y equals to simply Y equals to 1 if G is more than 0. Okay, and equal to -1 for G is less than 0. So at G equal to 0, it is sudden change. So that I can ignore. So there's a rare chance that you will get G equal to 0. But okay, to avoid these things, we can put any one value equal sign. Either equal sign I can put it here with the first one or second one. Okay. So you see, we'll compare between G and D. Then this E. So this E is becoming here D minus G. Based on this one, we want to train these things, these weights. So this is the exact difference between perceptron and Adaline. Okay, now rules for this perceptron is called Perceptron Rule, whereas the rules for this adaptive Adaline, so you know that Adaline stands for adaptive linear network or linear model. That's called, it is Adaline. So its algorithm is called least mean score algorithm, LMS, or delta rule. Okay, using least mean score algorithm or delta rule, we can tune these weights. Okay, now briefly we'll discuss what are these two rules. Okay, now for this perceptron, the perceptron rule is very simple. It says that if this y and d both are same, then there's no need to update the weight. Whatever it was the previous weight, the same will keep the same weight. Okay, we won't modify anything, the weights. So no update when output and d. And remember one thing, this perceptron and Adaline, the weights are adjusted sequentially based on the input data sets. Okay, so input data, so one feature vector x1 to xn, I'll get one corresponding output. Another feature vector again we'll consider next time, and we'll get corresponding output d, and that we'll consider for the next iteration. We'll try to tune it. So every time we'll consider one pair, input output pair, and depending on that sequentially we'll update. So it is more about stochastic gradient descent algorithm kind of things. So one data pair will be used to train the weights in one iteration. Next iteration, next data pair will be used. Okay, so all data pairs are not used simultaneously to train these weights. So it is also called online learning, okay, or sequential learning. So both are sequential learning. Remember, perceptron and Adaline both are sequential learning. Okay, so when the corresponding exact output y for one feature set is same as corresponding desired signal d, then there is no need to update its weights. But if there is any mismatch, then we should adjust it. So when output is less than d, then output is more. This is suppose previous output was wi, in ith iteration it was wi. Then okay, we can consider this thing better. So I is not ith iteration, I am calling it ith input. Okay, so this wi is corresponding sub w sub I is associated with x of I. Okay, that is one. So in one iteration, suppose that time it was wi, and then wi is modified to wi plus alpha times xi, and alpha is one constant. So wi should be replaced by wi plus alpha into xi in the next iterations. So it is replaced. Okay, so that is modification. So this is the modification here. Alpha times xi should be added. So you, and when y is more than d, when this output is more than d, then it is subtracted. Very simple. Now you understand that this y and d. So you see this y is again, it can take either 1 or -1. Similarly, d also can take either 1 and -1. No others. Okay, only two states. So obviously y less than d, this imply that obviously y equals to -1 and d equals to +1. Only one option. Okay, similarly when y is more than d, if I say obviously y equals to 1, whereas that time d equals to -1. Okay, so in that also you can say, just we can say that wi is replaced by wi plus alpha xi when d equals to 1. That's all. That's all sufficient. But remember, d equal to 1, but there's a mismatch between d and y, right? And again, this is true when d equals to -1. So this is when y equal to d, then there is no update. But when y not equal to d, in these two cases, y not equal to d, in that case, when d equal to 1, we should add alpha into xi. When d equal to -1, we should subtract alpha into xi. And alpha is between 0 to 1, equal to 1. And Rosenblatt used alpha equal to 1 in maximum experiments. Okay, so alpha equal to 1 is commonly used, though we can use alpha less than 1 but positive value, then also it will convert. So this is very interesting, very simple algorithm, but how it will converge? Sequentially it will adjust, okay, but it will give you the guarantee that in finite iteration it will converge. It will give you the perfect answer if it is linearly separable. Okay, these two classes are linearly separable. If data sets are linearly separable, then obviously this perceptron algorithm will converge in finite number of iterations. So it's interesting to understand what is the limit and how to get this algorithm, from where we are getting this algorithm, what is the basic idea. So everything will be discussed in one video in detail. Okay, so please keep watching. I'll be considering one video on Perceptron to get the idea about these algorithms, from where we are getting this idea, and what is the proof that it will converge in finite iterations. That will also be discussed in detail. Okay, next one is the Adaline, adaptive linear network. So you see, this is the difference. I told you that from here this G will be compared with D, and then using this error we'll try to tune these things. Okay, so how to tune? What is the LMS algorithm? So the algorithm is called least mean square algorithm or delta rules. Briefly I will discuss. So it's very similar. So Wi, corresponding Wi, should be replaced by Wi plus mu times, this is called one step size, E times Xi, and E is the error is this one, D minus Z is the error, and mu is called step size. Okay, and it is continuously updated. It's a rare chance that Z will become D exactly. Okay, but that is also not required. Suppose you know that when G is positive, then only Y equal to 1. When G is negative, then Y is equal to -1. Okay, so after hard solving operator, our objective is this Y should be same as D, not that D should be same as G. Okay, but if G is close to D, it is sufficient for us. That's the important thing. If G is close to D, then every time we'll get exact matching. D and Y will match exactly. Okay, so this algorithm is better than perceptron algorithm. It will converge in faster rate. Okay, and even though the samples are not linearly perfectly separable, then also it will give you some kind of adjustment of W, which will reduce the error greatly, and it could be used with some efficiency. Whereas this perceptron algorithm, if you use, and if the samples are not separable, then it will not converge at all. You can't use it. Okay, so we'll be discussing in detail. In machine learning, one thing I want to show, that machine learning, this same thing, Wi is Wi plus this learning rate is considered eta, and E is considered target output T, that is in our case D. Okay, and the output of this one is O. This actually G is there considering O, and target output is T. T minus O is this one, and corresponding input is XI. That's simple. Commonly we'll use this notation in machine learning. Eta times T minus O times Xi. O is the exact output of linear combiner, T is the target output, eta is the learning rate, and Xi is the corresponding input. Remember, it includes this input as well, bias input. For bias input, Xi is always 1. Okay? And other than bias input, all can have different inputs. Right? Not to say that x1, x2, this could be binary inputs. It could be non-binary. Any value it can take. Right? Okay. Now, what is today's artificial neuron? Now, this model, you see, it is very close to that one, Perceptron model. Only one thing is that here, this one, this threshold function, earlier it was a hard threshold functions. Now, this one, it's a active, we'll call it activation function. Some nonlinear function will be using here. And after that only we'll consider output, and this Y and D will be compared, and based on this error we'll try to tune these weights. It's not that from G, from this output, but remember this output is not the hard threshold output. Okay, so this activation, so what about this activation functions? Right? So this activation function is used to add nonlinearity to the network. That will be useful whenever you will connect many artificial neurons one after another to get a complicated neural network. That time, if you use this activation function, nonlinear activation, then only you will get some nonlinear output function mapping. Otherwise, linear combination of all linear neurons will give you only linear combinations. Okay, that is not desired. So to provide nonlinearity in our model, we have to include nonlinear activation functions. That is one objective, and this activation function should be differentiable. Okay, that is required. So exactly what is happening, we'll be using this several kind of activation functions. One is called sigmoid function, hyperbolic tangent function, ReLU function. ReLU stands for rectified linear unit. So left side it is made 0, negative side is 0, right side linear. So we'll be discussed all the activation function in detail in one video. So for time being, we'll say that there are several activation functions are used to provide nonlinearity in the today's artificial neuron, and we'll be using gradient descent kind of rule to adjust these weights. So you see the advantage of that algorithm that already we have discussed in detail, gradient descent algorithm. So again, I'll request all of you to go through my previous lectures about gradient descent algorithm. Okay, this will be much more useful. So we can use batch process, we can use mini batch, we can use this stochastic gradient descent algorithm. Okay, the versions we'll be discussing all those things in detail later. But this is all about today's neuron. Okay, and update rule is given by Wi using this gradient descent plus mu times the derivative of this function f, okay, times this error e times xi. That's all. So that's how I said that this activation function should be differentiable. Derivatives should exist. Otherwise, it is difficult to use gradient descent algorithm. Okay, so we'll be discussing this thing in detail. So in the upcoming video, what we will consider? I will try to go with the majority people asking for next topic in the comment section. So I request all of you to write something in the comment section, which topic you want. from my channel, that I'll consider first. Okay, so please write your comments in the comment section and suggest something. Okay, I hope you have enjoyed this video, and if you enjoyed this thing, please like this video so that other people can understand whether it is a good or bad. Please put the likes button if you have enjoyed this thing, and share with your friends or your juniors or seniors if you think it is suitable to share. And if you want to get my future videos on machine learning and other things, then please subscribe this button, and don't forget to press the bell button. Then only you will get immediate notification of my all videos, future videos. So I hope you will subscribe my channel. Thank you very much for watching this video.